On finite fields, right? F of x modulo f of x. Okay, great. Now let's continue. We will drop. So f is a field. Okay? Let f of x be an f of x. Have degree n. Let's say degree equal to 2. I mean, if degree 1 is the result would be obvious. Yeah. Then f of x has at most n roots in f. Okay? So if you have a polynomial in a field, over a field of degree n, then it cannot have more than n roots. Let's prove that. If f has no roots, if f of x has no roots in f, then the result is proved, right? Holds true. Okay? If the result is not, if f of x has no roots, then the result is true, right? Yeah.
Just for clarity, in general, when we have a polynomial, the indeterminate is also must exist in the field, right?
No, x, you mean x?
Yeah.
No, it could be, not necessarily. If you want to plug in a number, for x, no, it could be something, it's not necessarily in the field only. Okay, it could be a bit bigger. We'll see an example. So, if f of x has no roots, then the result holds true. Now suppose f of x has a root alpha. Then you can write f of x is x minus alpha times k of x for some k in f of x. Alright? Agree? Agree or not? Where the degree of k is n minus 1. Now what can we do here? How can we proceed here? By induction. Okay? Let's proceed by induction on the degree of f. We can proceed by induction on big F, on n, right? Yeah, are we good? On n? Yeah, on n. Great. So, if f of x, well, okay. So, if beta is a root of f of x, and beta is different than alpha, then beta minus alpha times k of beta is equal to 0. Right? Agree? Just plug in f of beta in there. Now, so since beta minus alpha is different than 0, and f is a field, then k of beta must be equal to 0. So beta is a root of k. At most n distinct roots. Well, let's see. You see that? You guys see that? Now we can set up our induction. So what would our induction step be here? Yeah.
Could you break up K to a similar expression?
Exactly. Is that here? My induction. Well, let's write it more properly. Let's write it more properly. I mean, should I do it or it's clear, right? It's clear. If any root is different than alpha, then it's a root of k. By induction, k has at most n minus 1 distinct roots. Right? I mean, let's write this. By induction, k has at most n minus 1 distinct roots. So f of x, k of x has at most n minus 1 distinct roots. Okay? Induction hypothesis. Okay, this is a bit clear. So really, if you're over a field, then a polynomial of degree n cannot have more than n roots. This breaks down if you're not over a field. Let's give an example. Yeah.
Wouldn't it be f of x has at most n minus 1 plus 1 distinct
And
roots?
thank you. And roots, thank you. Okay? So if you're not over a field, this doesn't hold true. Let's give an example. If you're not over an integral domain, this doesn't hold true. For example, take, let's see. And take x squared minus x. 0 is a root, right? 0 squared minus 0 is 0. 1 squared minus 1 is 0. Let's see. 2 squared minus 2, 4 minus 2. 3 squared minus 3, it's 6, right? 3 squared minus 3. 9 minus 3 is 6, which is 0. And then 4 squared, 16. 16 minus 4, 12. How many distinct roots do you have here? How many distinct roots do you have? How many?
At least 4.
4. Exactly. 2 is not a root and 5 is not a root. So you have exactly 4 roots. That works. That is not true anymore if the ring of coefficient is not a field. So you can have a polynomial of degree 2 that has more than 2 roots if the ring of coefficient is not a field. Or is not integral, but that's later. Okay, great. Now, great. Maybe, I'll mention something, I'll not prove it, I'll leave the proof as an exercise. I'll leave the proof as an exercise. So this one I'll do. Proposition. Let f of x in f of x be irreducible. Then, if f of x divides ax bx, where ax bx are in f of x, then f of x divides ax, or f of x divides bx. Just like for prime numbers, right? You remember this result for prime numbers? If p is a prime number and p divides a times b, then p divides a, or p divides b, right? The proof, exactly the same. What did we use for prime number? To prove this for prime numbers, what did we use? The GCD. Exactly. So we'll do the same here. Proof. So suppose f of x, so let f of x be reducible. And let f of x divide ax bx. Now if f of x doesn't divide ax, I mean if f of x divides ax, we're done. Right? Now if f of x doesn't divide ax, what can you say about the GCD of f and a is equal to? Then what is the GCD of f of x and ax?
1.
Ax is equal to 1, right? Agree or not? Yes or no? Yeah? So what can you write then? There exists ux vx in fx such that what? Such that 1 is equal to fx ux plus ax bx. Okay. Now what can I do? I multiply both sides by what?
bx.
Bx. The same proof for prime numbers, right? Let's multiply both sides by bx. Okay. Great. Now how do I prove that f of x divides bx? If f divides ax bx, what can I write ab?
Some multiple of it.
Some multiple of
Okay.
f comes k. Very good. So let's write it here. F of x is equal to ax. Ax bx for some k of x in f of x. Okay, great. So now I just can factor an f of x out. This is just f of x ux bx plus kx dx. And I'm done. Then f of x divides b of x. Okay? Now in general rings, this idea doesn't hold true. If you have this proposition, this idea of being irreducible and having this property is not true. Okay? But now if you have a Euclidean algorithm on the ring, then yes, you can do that. Okay? Great. I'll do one more theorem, and then I'll leave you the proof as an exercise. But I mean, all of this is non-examinable, okay? All of this is, I won't examine it. But if you're writing the deferred, then I might examine it, okay? If you're writing the deferred exam, then I might examine it.
The third exam?
Deferred. The deferred exam. Deferred. If you're deferring the exam, this material is examinable, okay? Great.
The third exam, that means just someone that takes it later?
Yeah, exactly. If, for example, God forbid you fall sick the day of the final and the service point defers it for you, then this material will be examinable. Okay? Great. Now let's do a theorem. I'll leave you the proof as an exercise. It's the same as for prime numbers, for integers. So let f of x be an f of x. Then f of x has an irreducible factor. Of degree say n bigger or equal to 1. of x an irreducible factor. How do you do that? We do this by strong induction, right? You remember this? If f of x is irreducible, then you're good. If f of x is not irreducible, we can split it into two polynomials of strictly smaller degree. You apply the induction hypothesis to these polynomials, right? You remember this or not? This is what we did for prime numbers. Okay, strong induction on it. Okay, great. Now, let f of x be a polynomial. Well, let f of x be an f of x. Of degree equal to 1. Then, there exists monic, irreducible polynomials let's use another, let's use L, say, f1 of x, f2 of x, fl of x in f of x, and positive integers. A1 up to AL in N, and an element A in F star, such that, now what does this one look like? You should tell me. F2 of x to the A2, FL of x to the AL. What does this one look like? Prime factorization. Exactly. This is we have a prime factorization in f of x. Yes?
Sorry, what does that say? Then there exists something.
Monic. Monic.
What does that mean?
The coefficient of the highest degree is 1. Okay? This is like the prime factorization, right? Yeah? You remember this? Yes or no? Do you remember this is a prime factorization? Just you do it in f of x. Moreover, if g1x, gkx are monic, irreducible polynomials in f of x, and b1 up to bk are integers, positive integers, and b is in f star such that what? F of x is equal to b g1 of x b1, gk of x bk. Then, what do I want to say here? In Z, the prime factorization is u. In how many ways can you differentiate a number into primes in Z? In how many ways can you factor a number into prime numbers? One way, right? The decomposition into prime is unique. And here it's going to be the same thing. Then b is equal to a. Then first of all, k is equal to L. B is equal to A. And after rearranging, G1 is equal to F1. GI is equal to FI. And AI is equal to BI. Okay? You just rearrange them. Once you rearrange them, you can match them. Okay? Great. Okay, is that clear? If you factor an irreducible polynomial into irreducible, there's only one way of doing it. There's only one way of doing it. You don't have many ways. Okay? The proof is left as an exercise and really is the same as for integers. The same idea. Okay. Now, proof left as an exercise. I mean, it's an induction argument, okay? The argument is an induction. Okay. And you use the previous proposition, like if f divides ab, then f divides at least one of them. It's like, you can follow the proof of the prime numbers. Okay, great. We'll finish. Let's see, we'll finish with two more notions. The Chinese remainder theorem for rings, and prime and maximal ideals. Okay? And then we conclude this. Sadly, or happily, I don't know.
Eventually.
So let's prove it. Let me write. The Chinese remainder theorem for rings. I'll prove it in 2 steps. One. Well, here, let R be a commutative ring. And let Ij be ideals in R. Then alright, I intersection J is an ideal of R, and R modulo I intersection J is isomorphic to severing of R mod I times R mod J to I plus J, which is defined as A plus B, where A is in I, B is in J, is an ideal of R. And if I plus J is equal to R, then R modulo I intersection J is isomorphic to R mod I plus R mod J. Okay? Note, I'll just do the corollary first. Let R be Z, and GCD Mn is 1. So let Mn be an N with GCD 1. What can you say about the ideal generated by M plus the ideal generated by M as GCD is 1? Is it the whole ring? If GCD Mn is 1, and you take the sum of the two ideals, if I is M and J is N, what is I plus J? Does 1 belong to I plus J? Could you write 1 as a combination of M and N?
Yes.
Yeah, so 1 belongs to I plus J. then I plus j is the whole thing. Right? If one belongs to an ideal, then the ideal is the whole ring. I plus j is R. And what is I intersection j in that thing, in that case? I intersection j, it's the common multiples of m and n. I intersection j will be the common multiples of m and n. If m and n are co-prime, the common multiples of m and n are what? Yeah. The common multiples,
Yeah, the multiple, not the
not the divisors. Yeah? But what are they?
and
The multiples of mn, right? If m and n are co-prime, the common multiples of m and n are just the common multiples of mn, right? So I intersection j, just m intersection n, which is equal to the ideal generated by LCM mn, which is mn, if mn are co-prime. Great. Apply the theorem. Z modulo mnz is isomorphic to z mod mz cross z mod nz. This is the Chinese remainder theorem for z. Okay? But proved another way. There is no characteristic involved here. Just rings. Okay, so I'll prove the theorem. And then we go for one last one. Proof. So I intersection j is an ideal, right? Okay, let's do that. So first, let phi, let's say, what do you want to call the homomorphism? I don't want to call it phi, because phi is it for something else. Let f, never use f for homomorphism, from R mod I to R mod j, be defined by f of r is just r plus I and r plus j. Now f is a ring homomorphism. What are the properties that I should check? Additivity and multiplicativity, and 1 goes to 1, 1, right? What is f of 1? F of 1r is just 1r plus I and 1r plus j, which is the identity of this product ring, right? The identity in the product ring is the pair of the identity here and the identity here. Now f of r plus r prime is just r plus r prime plus I and r plus r prime plus j, which is really r plus I plus what? R prime plus I times r plus j. This is how you define addition in the quotient ring. R prime plus j, and this is just r plus I, r plus j, plus r prime plus I, r prime plus j, great, which is f of r plus f of r prime. Now I have to check that f is multiplicative. What is f of r prime? This is just r prime plus I, r prime plus j. Well, what is r prime plus I? This is just the product of r plus I times r prime plus I times the product of r plus j and r prime plus j. This is the product of the quotient ring. Now, the product ring, the product is taken pairwise. This is just r plus I, r plus j times r prime plus I, r prime plus j, and this is just f of r prime, f of r times f of r prime. Okay? Now what's the kernel of this homomorphism? The kernel of phi kernel of f, sorry, is just the set R and R, such that f of R is 0 plus I and 0 plus j. So it's the set R and R, such that R plus I is I and R plus j is j. Well, really, this is just the set. When does R plus I is equal to I? This is just exactly when R belongs to I and R belongs to j. This is just I intersection j. So I intersection j is an ideal since it's the kernel of a homomorphism. I mean, you didn't really need that, but since we express it as the kernel of the homomorphism of f, then I intersection j is an ideal. Hence, I intersection j is an ideal of R. So that's the kernel, since I intersection j is kernel of f, and hence R of I intersection j is isomorphic to a subring of R cross I plus R cross j. This is the first isomorphism theorem. Okay? Yeah, okay. R mod I, yeah. Now let's look at 2. 2, the left, the proof that I plus j is an ideal is left as an exercise. Now all I need to show that, we will show that f is surjective in that case. We'll show if I plus j is equal to R, we'll show that f is surjective. And then we win by the first isomorphism theorem. Okay, so first, we know if I plus j is equal to R, then 1R belongs to I plus j. Hence, there exists A, B, and A and I, B and j, such that 1 is equal to A plus B. Okay? Now let's look at f of a. What is f of a? F of a is just a plus I and a plus j. Now a belongs to I, so what is a plus I? This is I, since a belongs to I. Now what is a plus j? A plus j, a is 1 minus b. A is equal to 1 minus b. This is 1 minus b plus j. So this is I, the coset I. B belongs to j, so b plus j is j, and this is 1 plus j. Right? A belongs to I, b belongs to j, and a plus b is equal to 1. Great. So I managed to hit 0 plus I and 1 plus j. Now similarly, what is f of b? What do you expect f of b to be? F of b is equal to 1 plus I and 0 plus j. Okay? Now I will show that f is surjective using this. Really, I mean, the way you should see it, I just need to get r plus I and r prime plus j. I need to find an element that hits these two, right? So let r, or let x, y be in R. We will find R in R such that f of R is x plus I and y plus g. Now really, I will write it another way. Maybe if I write another way, maybe it's going to be a bit clearer. Now write x plus I as x, write this way. x1 0 plus y 0 1. Okay, so what's a candidate for this? Let R be, I have to be careful here, let R be xb, bx plus ay. What is f of R? F of R is bx plus I. Oh, sorry, it's did I mess this up? I hope not. Is bx plus ay plus I and bx plus ay plus j. Now b belongs to j, right? B belongs to j. So bx belongs to j. So bx plus j is equal to j. Same thing for a. A belongs to I. So ay plus I is equal to I. So this is just bx plus I and ay plus j. Since ay belongs to I and bx belongs to j. Great. Now let's write this. What is that? This is just what is that? What is x plus I? Yeah. So this is just bx b plus I. Wait, what? What did I need to show? Yeah, b plus I times x plus I, comma, a plus I times a plus j, sorry, times y plus j. Okay, now what is a plus j? A plus j is equal to what? 1. 1 plus j, right? This is, and b plus I is equal to what? 1 plus I, right? Look at your notes from above. B plus I is equal to 1 plus I. This is 1 plus I times x plus I. And a plus j is 1 plus j times y plus j. Boom. This is just x plus I, y plus j. So f is surjective. And hence R mod I intersection j is isomorphic to R mod I cross R. Great. What time is it? I have 10 minutes. Okay, I'll just state the last two theorems. I'll leave them as an exercise. And then, yeah, it's okay. It's not a big deal. I mean, this won't be examined tomorrow or Friday. Not tomorrow, Friday. This won't be examined on Friday, but I have to do it. I'll just do one of them. I won't do all of them. I'll just do one. Okay. Maybe I could, and the proof is easy. I prefer to give you some tips about the final exam. Definition. Let R be a commutative ring. An ideal. P strictly contained in R is said to be a prime ideal. I mean, they do maximal ideal as well, but I will not do it. said to be a prime ideal if the following holds. AB belongs to P implies A belongs to P or B belongs to P. So if AB is in R and R and AB belongs to P, then A belongs to P or B belongs to P. Proposition P is a prime ideal in R if and only if R modulo P is an integral domain. This is not bad. This is actually not bad, okay? It's actually not bad. We'll finish in style and say that the proof is left as an exercise. It's not bad. It's actually not bad. Try to sit down and write it. And I don't know. I can't remember if they did it last year, but I'll just do it this year. P is a prime ideal in R if and only if R must be in. Do you want me to prove it? I can prove it. Yeah, let's prove it. I'll do one way. Which one do you prefer? If AB is a prime, which one do you prefer? This way or this way?
Yeah,
This?
towards the integral domain.
This way, okay. So A will prove this. So let P be a prime ideal. Okay. Now let say xy. So let x plus p and y plus p belong to R mod p. We'll show that R mod p is an integral domain. Be such that x plus p times y plus p is equal to, what's the zero element in R plus p? It's the coset 0 plus p, right? It's the coset p, 0R here. Okay, we'll show that x plus p is 0 or y plus p is 0. We'll show x plus p is 0p or y plus p is 0 plus p. Okay, now what is x plus p times y plus p in the commutative ring? This is just the product xy plus p is equal to 0 plus p. Right? This product here is this one. Well, this means that xy belongs to p. Oh, wait a minute. Since p is prime, then x belongs to p, or y belongs to p since p is prime. Hence, x plus p is equal to 0 plus p, or y plus p equal to 0 plus p. So R is an R mod p is an integral domain. We'll finish this the other way and say it's left as an exercise. Okay? The other way is left as an exercise. Okay. Left as a Christmas exercise. As an exercise. Okay? So this material is, no, I'm kidding, it's not examinable tomorrow. Great. So now the end is close to this. So first of all, I want to thank, well, 7 minutes. Let's leave this speech for the last 2 minutes. Okay? I mean, I could keep on going if you guys want.
What was the other definition of maximal something?
Maximal, yeah, I won't do it. I won't do it. But
Well, what is it?
a maximal ideal is an ideal that's not contained in any other ideal. That's it. So let us do it. Yes.
Do we have to know the converse of Lagrange proof?
For what?
That's what I wrote in my hand.
Yeah, converse of Lagrange for what?
I think
For P groups. No, you won't have to know the induction proof.
but
Okay.
what do we
Pardon me?
What do we
You need to know the results, and then I can ask you questions. Show, for example, that a P group has a normal subgroup of order P. I can ask you this. That's a very fair question. Okay, so I think we'll just end. So first of all, it was a big pleasure for me to teach this class. It's I mean, first of all, do you have any questions on the final, like the logistics or anything? Yeah?
Can we bring a calculator?
No, no,
Crib sheets?
no crib sheet, no calculator, no books. What you're allowed is a dictionary. Okay, if you need to translate the instructions, but I think you won't need one. But I said I allow the dictionary. Yes.
I haven't been reading the My Courses announcements, but did you already say like up to which lecture you're going to be covered on the final?
That was a long time ago.
Oh, okay.
Yeah.
My bad.
Okay. So on Friday, we stopped the proof at some point,
Okay.
and then we did all the calculations. We said from this point on, what we're gonna do is you have to know the statements, but not the proofs, and then you'll have some calculations to do.
Already 2 weeks ago, like last.
I don't
Friday, 2 weeks ago.
I don't know. I can't remember exactly the dates. I don't want to tell
Not
you the
last
dates.
week, but the week before, yeah.
I don't know. Yeah, I don't know.
Last-
Okay, so at some point we stopped the proofs,
Okay.
and then you have to know the results, and then you have to do basic calculation. Well, not basic, but calculations on those. Yes.
For longer proofs on groups, will the question be like reasonably broken up?
Yes.
So that,
I will break it up reasonably. I mean, you will see the practice final. In the practice final, I ask you first question, state the three Silos theorem. Question B, prove one part of the Silo third theorem. I might not ask you the entire thing. Okay, so I will ask you, for example, the practice final, I ask you show that NP is congruent to 1 month in. I will not ask you the entire thing.
So, like something like question 3 on homework 8, or question 3 on homework 8.
Question 3 on homework 8, what is that?
Something like, it's the one where you have to see where you have to treat the orbit of one thing as a transit G set on its own, and then you use a few other theorems from before in the homework.
Yeah, that's fair.
Like, is that fair? Like, would you ask us that in steps, or?
I might do it in steps, or I might give you a hint.
Okay.
Okay. Yeah. No, there are 3 hints in the final. In the final, there are 3 hints for things that are, I would assume, not very difficult. Just to to help you out, if you need, just to give you the right, just to give you to point you in the right direction. Okay. Now I released the homework in this class, the homework grades. As I said yesterday, the median is 100. The median of the homework grades is 100. For homework that are not hard, for homework that are supposed to be very challenging, and yeah, so the group is pretty strong. Yeah.
If you get how does it work if you had 100 and then you chop off the?
I explained it. I explained it 25 times. Okay, so I mean, I'll just take your grade on I'll do the calculations and then it will be clear. Yes.
What happens with the bonus? If
I didn't grade it yet.
yeah, but once you will grade it, what will happen with the extra points?
I said they will count as extra points.
But the overall grade?
Yeah. Yeah, on the homework grade, you can override the homework grade. Yeah.
No, but that means that leaks into the other percentage in the
Other
whole
way.
class.
Yeah. I mean, so I explained it. I'll take your homework on 350, and then the bonus will be added to it, and it will still be on 350. So you can get up to 2 extra %. A bit more, maybe slightly more. Okay, so this class has been a very good class. It's my first time teaching it. Well, I don't know if it's gonna be the last time, but
It's gone well.
but I hope so. I hope I put some effort into this, just to teach it in a way that maybe it hasn't been taught this way before. And you guys have been awesome. Your grades reflected, and then, well, the attendance the last few weeks has been good. So I wish you good luck in the rest of your finals. And yeah,
Do we need to know how to do induction for the final?
yeah, you need to know how to do. You need to know how to do induction.
So if you know, will it be on the final?
I mean, yeah. You need to know what induction is, right? I will not ask you show that 1 plus n, 1 plus 2 plus n is n plus 1 over 2. I will not ask you that. Okay, so yes. Pardon me? Yes. So yeah, thank you very much. Yes. I asked someone to remind me maybe. Yeah. So please fill in the course evaluations. The course evaluations are very important to me, just to see what went wrong, and they're anonymous. So the course evaluation, I don't see your name, and they're not released until after I submit your final grade. So the math department has a policy that the course evaluation should be done before the final exam period. So I think today is the deadline. Is today the deadline? Today is the deadline for your math courses to fill evaluations. I don't know for other courses, but please it's good that you fill them in. And please for 235, please take 5 minutes to fill it and write comments. I usually ask some questions. I added 2-3 questions to the evaluation if it was, but please take the time to fill it in. It's good to fill it now because you won't have the chance to fill it later. And I think for now, someone told me it's 25% the rate of evaluations. So please, if we could raise the rate a bit so that you know so that you know you fill it in. And then I have 2 extra review sessions / office hours today and tomorrow, 6 to 7, 6 to 7. You don't need to come in person. I'll just stream it online. It will not be very long. I'll just finish the exercises on rings. By the way, and yesterday's rings is very important. So please make sure to view the session. Yesterday was very good. Actually, everybody answered questions. So which is very, very good. Many people answered questions. So it was yes.
You couldn't really hear the people asking the questions though.
Yeah, so it's I tried to repeat, but I forgot sometimes. But the answer should be clear. Okay, thank you everyone for everything. Thanks. I'll see you Friday. Thank you. Thanks. Let's make sure I record this, the clap.